Hi, everyone. Welcome to our talk. My name is Rituraj Singh, and I'm a software engineer in the AI training team at Bloomberg.
And I'm Jin on the AI inference team from Bloomberg.
Loading models for AI training and inference is a well-known bottleneck. In this talk, we'll talk about caching models and show how it helps in saving time and compute resources in a cloud-native AI infrastructure. So let me start with a quick overview of what we'll cover today. I'll begin with a brief look at AI at Bloomberg and the infrastructure that powers it. Then we'll dive into our model cache design and show how it's implemented in training and inference workloads. We'll also show how we federate caches across Kubernetes clusters using an open source tool called Karmada. We'll talk about Karmada in the later slides. Finally, we'll wrap up with a demo and look at the practical benefits of caching these models. But first, let's look at Bloomberg. Bloomberg is a global financial technology company known for the Bloomberg Terminal. It's a software that delivers a diverse array of information, news, and analytics to facilitate financial decision-making. The terminal gives access to real-time market data, insights, communication tools, and research at a vast scale. And Bloomberg uses AI to sift through massive volumes of information, both structured and unstructured. And this provides our clients with meaningful insights and enhances the efficiency of their financial workflows. Now, these are a few of the domains where Bloomberg uses AI. We use extraction to surface information from unstructured financial data. That data is then enriched to make it more discoverable and actionable. We use AI search for pointing to relevant content, and we also summarize news and research to generate financial signals. All of this to help our clients make better and faster decisions. OK, so the backbone of AI at Bloomberg is its data science platform. It is Bloomberg's unified AI infrastructure platform and a one-stop shop for everything machine learning, large-scale computation, and data science. Built on top of Kubernetes, it's a multi-cluster, multi-tenant system that provides scalable infrastructure for both training and inference, including GPU support. And it delivers a full MLOps experience, right from data exploration, model development, fine-tuning, versioning, and deployment of inference services. And under the hood, we integrate with several open source technologies like KServe, Karmada, Argo, and Jupyter, just to name a few. Now let us walk through the journey of a model on the data science platform. So say you're a machine learning engineer and you want to fine-tune an LLM. First, you would need to create a configuration for your training job that specifies the compute resources and the training strategy, whether it's like single node or multi-node, and also the framework like PyTorch. Now, this is accomplished using Kubeflow Trainer, an open source project that provides Kubernetes native training workflows. And once your training job configuration is ready, you're ready to submit the job. The job goes through a multi-cluster orchestrator called Karmada. It's an open source tool which determines the best GPU cluster that can accommodate the request of your job. We'll also talk about Karmada. Now, once the job is submitted, the training starts, and after the job completes, you'll have a fine-tuned version of your LLM. Now, you would want to use this LLM and serve prompt requests to generate tokens. So how would you do that? To do this, you would create an inference service. An inference service runs on KServe. It's an open source Kubernetes native inference platform that can use VLLM as its serving engine. And once you have this inference service, you'll have an HTTP endpoint that you can hit to access your LLM and generate tokens out of it. And once this endpoint is ready, it's now ready to get integrated with the Bloomberg terminal. OK, so now let's talk about one of the bottlenecks. And that is the core part of the talk, model loading. Fetching large language models from remote storage takes time. And that time grows with the size of the model and also depends on the network bandwidth. For example, loading a 70 billion parameter model can take several minutes. If you have a 600 billion parameter model, that can take much longer, especially if the storage system is under pressure. Now, that could be a problem. During peak inference load, these delays can impact performance. And in continuous training or fine-tuning scenarios, frequent model reloads can be slow, wasting compute and stretching job runtimes. So the question is, can we cache some of these models for our training jobs and inference workloads? And that is what we are going to answer today. And with that, I'll pass it off to Jin to talk about inference.
Cool. Yeah, thank you, Rituraj. So let me first talk about KServe and inference services. So KServe is a model deployment, model inference platform on top of Kubernetes. It's first started here at Bloomberg. So users can provide an inference service spec, and then KServe will create the Kubernetes deployment and service, and then users can call that endpoint to get the inference service response. And this is an example of an inference service. So the KServe creates 4 pods, so 2 pods on each node, and each pod have access to the GPU, and they are running VLM under the hood. So let's talk about the inference service startup problem. So this is an example for a 70B large language model. So first, we need to download the model from the model storage. In this example, it takes about 12 minutes. And then it takes another 2 minutes to download this VLM Docker image. And then it takes up a couple of seconds for the VLM pod to start up. Once the pod is running, it will load the model from the local storage to the GPU memory. So overall, it takes about 15 minutes just for the service to start up. But if we cache the model on the GPU nodes, we don't need to fetch the models from the remote model storage, and we can just simply load the model from local disk. So notice that for the second step, we don't have to download the VLM image every time. So for each node, we only need to download it once, and then the image will be cached. So overall, it will take only about 1 minute to deploy this service if the model is cached locally. So this is a huge speed up, like speeding up from 15 minutes to 1 minute. So now let me dive into the design and implementation of this model cache component. So model cache itself is a Kubernetes controller. And if you're not familiar with Kubernetes, this is how a Kubernetes controller works. So the controller will compare, it runs a continuous loop that compares the actual state in the cluster and the desired state from the spec. So for example, if as a user, I update the pod spec to like from 1 replica to 2 replicas, the Kubernetes controller will create another pod so that we have 2 pods running in the same cluster. So we have our own model cache custom resource and our model cache controller that's reconciling this resource. So this is the example of the model cache resource. It has the source model URI, which is where we download the model from, and the model size, and then the node group. So what is a node group? A node group is just a selection of nodes. You can you can specify the node selector to select a particular GPU type, and you can specify the local path. So that's the location where we download the model to. So now we have the model cache controller. This is how we actually cache a model locally. So on the left side, the cluster admin creates this model cache resource. And on the right side, we have our Kubernetes cluster with 2 GPU nodes, and each node have a fast local disk, like NVMe disk. So now the user creates this this model cache resource in the Kubernetes cluster. And then the model cache controller creates 2 jobs on each node. So it will the jobs will be downloading the model. So now the jobs are running, and each job is downloading the model to its node. So now the model is, after a few minutes, the model is available on these 2 nodes. Now, when you create an inference service, the model cache controller will create this persistent volumes, which can be attached to the pod. So the pod will have access to the local disk. Now it doesn't have to download the model from the remote storage. So just a quick recap. This is the responsibility of the model cache controller. So on the left side, it watches the model cache resource, and on the top, it creates the model download jobs. And then once the user creates an inference service on the bottom, the model cache controller will create the persistent volume on the right, and then inference service controller, which is KServe itself, will attach this persistent volume to the inference service pod. So now the inference service pod will be loading the model from local disk. And we are also tracking the status on the model cache resource. So this is an example of 4 nodes. So we have this model cache on all of these nodes. So on the left side, on the status section, we have the available number of replicas and the inference service that's using this cache, and also the status of each node. So yeah, everything looks good, right? Like we have the models, we can deploy the inference service quickly, but what can go wrong here? So here's a scenario, right? At 9 a.m., model is cached on these 2 nodes. Everything's running normal. And then 1 minute later, something happened to 1 node. And for some reason, we have to rebuild this node, basically doing a factory reset. And the node, like all the models on the local disk is wiped out. But we still need the models there, like because we still want to deploy the inference service on that particular node. So we added another component. It's called the node agent. It's running on all these GPU nodes. So it's basically checking the local disk continuously, like once per minute, to be exact. And if the model is not on the disk anymore, it will recreate the download job and to re-download the model from the model storage. So now the model cache controller is not responsible for downloading the model on its own. We have another internal resource, like basically for each node we have a specification of like all the models to download. So the model cache controller creates this spec, and then the node agent will pick up that spec and download all these models. So for the same scenario, at 9 a.m., everything's running normally. And at 9:01, there are some issues with the node. And 9:04, we put the node into maintenance. And at 9:10, when the node comes back, it doesn't have the model anymore. But now we have the node agent running. So the node agent will recreate the download job, and the download job will be downloading the model again from the model storage. So a few minutes later, here at 9:15, the model is back on the local disk. So the pods can use the local model again. So same scenario as before. Like on the right side, we are showing our intermediate resource, like local model node resource. It has all these like a list of models that's expected on each node. So now Rituraj is going to talk about the model cache for fine-tuning.
Thank you, Jin. So that was model cache design for inference. Now let's talk about LLM fine-tuning. So let's say you want to fine-tune a model. And well, the first step is to fetch the model from remote storage into your cluster where you want to run your training job. It can take several minutes for this model to get downloaded, depending on the model size and the network bandwidth. The second step is that you'll pull your fine-tuning code from a Docker registry. You'll create your training job configuration and then submit the job into the GPU cluster. Once your job completes, you'll have a trained version, a fine-tuned version of your LLM. So it looks good. However, if you use a cached model, you can save that time that was previously spent on fetching the model into the cluster. This will not only kick off your training job sooner, but it will also prove to be compute efficient. And as multiple models are fine-tuned, the cost benefit increases. Okay, so in our training platform, we use model caching that is baked into KServe. A question that you may ask is that KServe is an inference platform, so how do we use it for training? We only use the model caching part of KServe. And to achieve that, we first decoupled the model cache resources from other KServe components, and only kept the model cache custom resource definitions and controllers. Then we enabled a flag called disable volume management, which we added to KServe, which basically turns off KServe's ability to manage PV and PVCs, persistent volumes and persistent volume claims. And this allows a user or an admin to write their custom logic or custom controller for their own particular use case, depending upon their multi-tenant environment. So instead of inference pods, the model persistent volume is now attached to the training pods. Now let us talk about an open source multi-cluster orchestration system, that's a mouthful, called Karmada. To give some context, many of you may know that a pod is the smallest deployable unit in Kubernetes. Containers run in pods, and Kubernetes manages these pods. To manage multiple Kubernetes clusters from a single control plane, we have something called Karmada. So how does Karmada enable multi-cluster Kubernetes resource management, all from a single control plane? You can imagine Karmada as the control plane that manages multiple clusters. Now imagine this. You can submit a resource to Karmada. Maybe it's a job, a deployment, a secret, or even a custom resource. Karmada would accept it just like Kubernetes would. But instead of just scheduling it locally, Karmada's job is to figure out which cluster this resource should go to and how it should behave when it gets there. At this point, Karmada associates the resource with the propagation policy, or a cluster propagation policy if it's a cluster-level resource. This policy defines where the resource should be deployed, maybe one cluster or like several clusters, and it can even define the placement logic. So if you want your placement logic to be dependent on certain labels or certain annotations, you can do that in Karmada. If you want more fine-grained control, you can also set override policies. All right, so once the placement decisions are made, Karmada creates something called as a resource binding. This acts like a tracker, and it tells Karmada what resource needs to be deployed where and monitors its status over time. And finally, Karmada generates a work object, and this is the actual manifest that gets pushed down to the member clusters. So this is what makes Karmada powerful. From a single control plane, you can deploy resources across clusters, you can create propagation policies, and you can track resource status everywhere. This design of Karmada helps in seamless management of multiple clusters from a unified control plane. On Bloomberg's data science platform, Karmada plays a key role in scheduling training workloads. It is used as a multi-cluster orchestrator that performs workload estimation to smartly determine the right cluster that can accommodate your ML jobs. So if you look at the image on the right, you can see that a user is submitting a job to Karmada, and then Karmada determines what's the best cluster to fit that job in. This ensures that both clusters are well utilized and there's optimal GPU utilization. So a question that you may have is that, what about resources or services that were running before we adopted Karmada? For that, Karmada has a CLI tool called Karmada CTL Promote that can easily promote resources from member clusters and bubble them up to the Karmada layer at the federation level. Finally, a key property of Karmada is that it propagates resources really well. And that is what we use for model caching as well. If you're interested in learning more about our adoption of Karmada, please check out these talks from previous KubeCons. Now, this is an example of a propagation policy. As local model cache is a cluster-level resource, we have a cluster propagation policy. In the spec, you can see that there's a placement section with a cluster affinity for two clusters. There's cluster A and cluster B. In the resource selector section, we have local model cache. What this propagation policy is really telling Karmada is that if you get a local model cache resource, and if it has the label, my custom label with the value sample label, then please propagate this to cluster A and cluster B. OK, so now, once the model is propagated to both clusters, how can we get the status of the model cache from Karmada? Now, if you remember from the previous slides, each resource submitted to Karmada has an associated resource binding or a cluster resource binding. This resource binding also tracks the aggregated status of the resource across all the cluster where it has been propagated. In this example, you can see that we have this model cache that has been submitted to two clusters. There's cluster A and cluster B. And for both of these, we have the node status and the available copies of the model. Okay, so for ease of use of users of the data science platform, we built a service called the Model Caching API. This API allows the data science platform user to perform CRUD operations like creating model caches, deleting model caches, and also fetching the status of the cache. As a user, you can submit a request to cache a model. You can define the model's remote path, the GPU types where you want to cache the model, and also the whether it's for like training or inference. Okay, so once this request is received by the API transforms the request into a local model cache object and forwards it to Karmada's API server. Karmada then applies propagation policies to place this model cache into the desired clusters. And once the model cache controllers on each member cluster reconciles, the model gets downloaded. As a user, you can hit the model caching API to fetch the status of your cache model. And to fetch the status, the API gets the cluster resource binding, which includes the aggregated status. And this also shows the download status of the model. So you can see that in the response, you have the GPU types, you have the model size, and you also have the number of failed nodes and the ready nodes with this model. And with that, we'll talk about model cache on the cloud.
Yeah, we talked about model cache on local nodes, which is on the left. So the model cache controller is responsible for creating the persistent volumes for each node and like managing the download. And on the cloud, many cloud providers provide these fast storage that can be attached to the pods. So we can extend the model cache controller to make it work for the cloud environment. So here is an example. This is actually a KServe issue on GitHub. So this is basically a feature request for model cache controller to integrate with Alibaba Cloud. So they provide the data cache and the image cache, and we could extend the model cache. Extend the model cache controller to create these caches by talking with the cloud providers. And now with model cache, one important use case is auto-scaling. So with KServe 15, we support auto-scaling based on custom metrics like token throughput. So this is more suitable for like LLMs, so we can make more efficient use of our GPUs by combining auto-scaling and model cache. Okay, so now let's do a quick demo for actually caching a model and then deploying inference service and then scaling up an inference service. Let me go to this video here. Okay, so this is my personal laptop. So I have a kind cluster. In this kind cluster, we have 2 workers. And if you I'm mounting my local folder, like this models folder, to the kind clusters, to each node. So this is an example model cache resource. Basically, this is saying I want to cache this model from Google Cloud on all my worker nodes. And now I'm creating this model cache resource in my Kubernetes cluster. So we have created 2 download jobs for each node. So they are running right now. And now it's completed. So you can see on the top, in the Finder, we have this small model already downloaded. And you can also see the status on the model cache resource. It says node downloaded for both nodes. So now let's create an inference service. So this is a KServe inference service. You can specify like a predictor, model format, and then the storage UI. I'm using the same storage URI we just cached. And notice that for the user doesn't need to change anything for the model cache. Yeah, they can still use the same inference service back. Now I'm creating this inference service, and it's already running. So I can go to this pod and check the pod spec. Yeah, so in the pod spec, you can see it's automatically attaching this mount path on the node. It's models/arrays. Yeah, that's a quick demo for the model cache. Okay, so now I'm doing another demo. So this is running on an actual GPU node. Yeah, so we already have the model cached. This is like a 70B large language model. So I can create this inference service directly. And now the pod is already running, but it's not ready yet because it's loading the model from local disk to the GPU memory. Yeah, so it will take some time, about 45 seconds. Yeah, just a few more seconds. Now it's ready. It's ready for inference requests. So I have a Python script that's running, like sending a lot of requests to this endpoint. So now I'm running this script. It's like it's sending the chat completion requests. And now you can see it's scaling up. It's creating a few pods. And yeah, all of these pods will take about 45 seconds. Yeah, it's creating the last pod. So compared to like not using model cache, it will take like over 10 minutes on some scenarios. So this is a huge speed up in our environment. So with model cache and auto scaling, we can like make more efficient use of our GPUs. Yeah. So now only one pod. Yeah, it'll take a few more seconds for the last pod to be ready. Okay, cool. So that's it for this demo.
Thanks, Jin. So as you saw, if you did not use a model cache, it would have taken about 15 minutes to scale those inference services. And with model cache, it takes about 45 seconds for each pod. So to close it out, we saw that caching large models has multiple benefits. You can rapidly auto-scale inference services, you can recover from pod failures quickly, and you can reduce time for fine-tuning jobs. With model cache, you can also debug your training jobs faster, because now, with model cache, your training code is going to enter the training loop at a sooner rate, because now it's not wasting time to fetch model cache, the model from the remote storage. And you can also debug your inference services configuration, as the iteration is going to be much faster with a cached model. And finally, you save valuable GPU hours, which can be fully used for actual model training and inference. A shout out to all the open source maintainers of KServe and Karmada who make this possible. And we look forward to more open source contributions that can enhance the AI training and inference ecosystem. Also, Bloomberg Engineering is hiring across various domains. So if you find a relevant position, please feel free to apply. And with that, thank you so much, everyone, for attending our talk this evening. And now we're open for questions. Yeah.
Yeah, sure, I can take it. So the question is like, how does the cache work with EC2? So we haven't implemented this yet. So this is one thing we want to explore in the future. So currently it's mostly for our on-prem instances, like our own GPUs. Yeah.
I just want to add to that. So basically all of the model cache resources, the CRDs and the controllers, these are Kubernetes native. So theoretically, it should work on something like EKS, which is like Elastic Kubernetes Service on AWS. But that's something that we have to explore. Sorry, what's the question? EFS versus EBS. Do you like to comment on that?
Yeah, that's a very good question. We were planning to do some benchmark, but we haven't done this yet. I think like S3 have some they have some custom storage CSI drivers or something that's also providing some cache. So we haven't actually done the benchmarking yet.